I've got a book, if you've got a pen.
Absolutely, Matt. Let me show you one of the spectacular results of relativity theory. And let's do a little thought experiment. Suppose here is Matt 1, standing on a train platform.
Okay.
And here is Matt 2, just call him Matt, standing on a train. And he's moving along with some velocity, call it V, relative to the Matt standing on the platform. The Matt on the moving train is wearing a wristwatch, and his time, call it T prime, and call the times of all the clocks on the platform T. And what we want to do is to compare the time on Matt's wristwatch with clocks that remain at rest on the platform. They all read the same time.
But I'm going to assume that even though the clocks are at rest and my clock is moving, that they're all the same.
They're all the same.
Clocks always tell the same time, if assuming they're all synchronized.
Yeah, one would think so, yeah. And let's call the Matt on the train...
But you're going to show me that they don't move?
I'm going to show you that they don't, convince you that they don't.
T prime and T.
And T prime and T. Now, it turns out Matt on the train's time, T prime, is equal to T times the square root of 1 minus V squared over C squared.
So the time here is equal to something complicated. It's not just the same as that time.
No, it's not the same as that time. Your time is not the same as my time. These two times are different, and your time is...
If I understand the equation correctly, it says something unbelievable. That time runs at different rates, depending on how fast you're moving. Take a train zooming through a station. This equation predicts that a clock on the train, reading time T dash, would run slower than clocks reading time T on the station platform. I've never noticed it, and here's why. This bit of the equation is what makes the two clock times different, but it only has a significant effect if the velocity v of the train is very fast, close to the speed of light. And if the train could reach the speed of light, you get 1 minus 1, which equals 0. And then t dash equals 0. Relative to the platform, time on the train completely stops. This stretching of time seems impossible, but according to Arthur, it's been proven by practical experiment.
Now that's really something, that's wild. And he realized that's because time is a relative quantity. Just as I discussed with you.
Right.
That your time is only the same as my time if we're standing still next to each other.
Yes.
But if you go away and come back, your clock, although it would be very difficult to perceive it, will read a slower time than mine.
Well, I'm taking in a lot of what you're saying so that I'm far more informed than I was before you spoke.
Good.
But the thing that's really big for me is this idea of the physical nature of time. And that seems a marvelous idea.
Oh, it turns out that there's not space and time, there's space dash time.
Right.
In other words,
they are
that's right.
a single entity.
Is single entity.
The right word?
Time and space are connected by the velocity of light.
That was definitely the hardest equation so far. Not just the maths, but because of the ideas it contained. You might be worrying about time on a tube train, but you wouldn't think time was actually changing shape. Einstein worked out that time and space are inextricably linked through the speed of light. That was a thought that it was simply impossible to have before. Reality had changed, and Einstein did it with equations. I'm beginning to get a crush on science.